This video, this lesson is now going to involve calculations and the conceptualization of what is a measure of dispersion. Okay, so again, in terms of quantitative analysis, finding descriptive statistics, a measure of dispersion is intended to be a complement to a measure of location. Measure of location tells us where the center of the data set is located. Okay, and measures of location, right? Where's the center? Where is the average, right? Where is the center of everything found? And then dispersion, right? The word dispersion means how spread out something is. So in other words, a measure of dispersion is telling us how spread out is most of our data. The obvious example, the easy analogy for what we're getting at, right? A measure of location and a measure of dispersion. Take two people driving in a car, one uses cruise control and the other has a very volatile driving speed, right? They speed up, they slow down, they speed up, they slow down. Okay. The measure of location, both individuals on average drive 70 miles an hour on a highway, right? They have the same measure of location. The center of their data is located at 70. Okay, so they have the same average. But the person who uses cruise control effectively has zero dispersion, right? Their speed, their velocity is not spread out. They stay at 70 almost the entire time. Conversely, somebody who speeds up and slows down and speeds up and slows down, right? Somebody who is very erratic, that individual goes from 50 miles an hour to 90 miles an hour to 60 miles an hour to 80 miles an hour. So on average, they drive 70, but their velocity is much more volatile, right? So in other words, their dispersion, how spread out is their speed? Their dispersion is much more spread out than somebody who drives, with cruise control on. Okay, so measures of dispersion tell us how spread out our data set is. And now we're going to look at how to calculate these using our whiteboard. Okay, so for measures of dispersion, this tells us how spread out the majority of the data is. How spread out the majority of the data within a probability distribution. Okay, so this tells us how spread out the majority of data within a probability distribution is. And again, there are three measures of dispersion that we're going to work with in this class. Okay, the first one I put all the way up here. It's called the range. Okay, range is going to be a very easy one. It's going to be, the calculation is going to take us 2 seconds. Okay. And then I put 2 and 3 down here because they are very, very related to one another. In fact, one is simply the square root of the other. And those two are the variance, and the standard deviation. Okay. The standard deviation is nothing more than the square root of the variance. So in other words, if you calculate the variance, you get that number, take the square root, now you have the standard deviation. Okay. So those are the three measures of dispersion. The range is very simple, as we'll see, but it's better than nothing, right? But it's very very quick to calculate it. You can work with the range very very quickly. But the two that are used the most, the variance and the standard deviation, normally the standard deviation is the big one, right? So in terms of our measures of location and measures of dispersion in this class, we're going to be working with the means for location, and then the standard deviations for dispersion. Okay, but obviously, in order to get the standard deviation, you have to get the variance. So, sort of, once you have one, you obviously have the other. Okay, first, let's calculate the range. Let's take our IBM stock prices again. And if I remember correctly, we had 92, 90. That's not a 95. We had 92, 95, 104, 98, and 107. Okay. If the order is not, if it's out of order a little bit, that's fine. Okay. So the range is a very easy one to do. The range is simply the maximum value minus the minimum value. Okay, maximum value minus the minimum value. What's the maximum value? Well, 107. What's the minimum value? 92. So let's just do 107 minus 92. And that gives us 15. Okay. So that tells us that the spread, right? How spread out is the majority of data within our probability distribution? The majority of the data, excuse me, is spread out $15. Okay. At a maximum, it was $107. At a minimum, it was $92. So there was a range of $15. It's just the maximum minus the minimum value. Okay. So that's the first measure, right? First measure of dispersion is the range. And again, just max minus min. It's pretty easy. Okay. But the more common ones that we're going to work with are the variance and the standard deviation. So let's pull up a new page on our whiteboard. Okay. I'm going to recreate our IBM stock prices. Okay. 92, 95, 104, 98, 107. Okay. And now let's work with variance. Remember, in order to get the standard deviation, you have to get the variance first, right? The square root of the variance turns into the standard deviation. Okay. Now, just like with the arithmetic mean, right? Just like with the arithmetic mean, there are two different variances, right? Remember the mean, there was the population mean and the sample mean. Well, here for the variance, we have the population variance and we're going to have the sample variance. Okay. So for this, now we're going to calculate the population variance. Population variance is sigma squared. Okay. That is a funny looking zero or so. That is a Greek letter, sigma. That is lowercase sigma. Okay. It's a zero with kind of a tail coming off the top. That is lowercase sigma, Greek letter. If you want to look it up, just Google lowercase sigma, S-I-G-M-A. Okay. So sigma squared is the population variance. Okay, sigma squared. This is a Greek letter, sigma, which means that it or indicates that it is a population parameter, right? It's a characteristic of a population. Anytime we're working with Greek letters, we have parameters. sigma squared population variance, okay? And just to be clear, this is lowercase sigma. Lowercase sigma is the population variance. Capital sigma, you may remember, stands for, or uppercase sigma, capital sigma, stands for summation. Okay. And that's going to be in this formula as well. Okay. I just want to clarify, just the same way there's capital A and lowercase a, there is in the English alphabet, there is capital sigma and lowercase sigma in the Greek alphabet. And capital sigma stands for summation, lowercase sigma stands for the population variance. Okay, so sigma squared is the population variance. This is a characteristic of a population, it's a parameter. Sigma squared is equal to the summation of x minus mu squared divided by capital N. Okay, so I'm going to show you what this formula means in a second. I'm going to show you how to expand it. But what this is saying is summate all of the terms x minus mu. So you have to do x minus mu squared divided by capital N, which is the number of observations in the population. Okay, number of observations in the population. Now, here's like a trick. When you go to expand this, however many parentheses, or how many parentheses do you need? However many observations you have, 1, 2, 3, 4, 5. However many observations you have, that's how many parentheses you need to have when you expand and calculate this formula. Okay, so what we're going to do is we're going to get 5 terms. We're going to get 5 parentheses. X minus mu squared, okay? And then we're going to summate those 5 terms and then divide it by the number of observations we have, which is 1, 2, 3, 4, 5. Okay, here's how we do this. What this formula is saying is x1 minus mu squared. At least if I could get a better one there. Okay, plus x2 minus mu squared plus x3 minus mu squared plus x4 minus mu squared plus x5 minus mu squared divided by 5. Okay, 1, 2, 3, 4, 5. Okay. So that's how we're going to calculate this. Now, let's go back to the top, right? Sigma squared, okay, the population variance. Sigma squared is equal to the summation of all of the x minus mu terms, x minus mu squared terms, right? You got to add these all up divided by n. So there's going to be an x minus mu squared term for x1. There'll be another one for x2. There'll be another one for x3, another one for x4, another one for x5, okay? This is x1, 92 is x1, 95 is x2, 104 is x3, 98 x4, 107 x5, okay? So let's calculate this. Well, the first problem we have is that we need to know what mu is, right? We need to actually get mu, the population mean. You may remember that mu is equal to the summation of x divided by capital N, which is equal to 92 plus 95 plus 104 plus 98 plus 107, which broke out to 99.2. Okay. So mu is going to be 99.2. Okay. Now that we know mu, we can start calculating this. So sigma squared is going to be equal to 92. And this could be a sizable calculation, okay? But that's all right. This is just arithmetic. It's not really math. Arithmetic is just adding and subtracting, okay? 92 minus 99.2 squared plus 95 minus 99.2 squared. See if I can make a better 2 there. Not really. Plus 104 minus 99.2 squared plus 98 minus, sorry, nope, I was about to write the wrong thing. 98 minus 99.2 squared plus 107 minus 99.2 squared divided by 5. Now, we're just going to calculate this. Okay, this becomes equal to 92 minus 99.2. This is negative 7.2 squared. And I'm going to work in small steps. I'm going to work in every step slowly, right? I'm going to go step by step through it. I'm not going to try to combine multiple steps here. Okay. So, but remember, please excuse my dear Aunt Sally, right? Parentheses, exponents, multiplication, division, addition, subtraction, right? Work through the order of operations. If you do the order of operations with any arithmetic problem, you will always get it right. Okay. Just work slow and steady. The tortoise beats the hare. Okay. 95 minus 99.2 is negative 4.2 squared plus 104 minus 99.2 is 4.8 squared plus 98 minus 99.2 is negative 1.2. Oh, almost forgot the square. Let's see. 107 minus 99.2 is 7.8 squared divided by 5. Okay. Now, we're just going to have to start squaring these. Okay. The squares are going to get rid of the negative numbers. Remember, when you square something, right, this is so negative 4.2 squared, that is negative 4.2 times negative 4.2. That is not negative 4.2 times 2. Okay. That's when you're squaring something, you're multiplying that a number by itself. So negative 4.2 times negative 4.2. That's what the squares are saying. Okay. So we have, if my phone wakes up, there we go. Okay, so negative 7.2 squared is 51.84 plus, see if I can turn it this way. I'm just trying to use my calculator. There we go. Negative 4.2 squared is 17.64 plus 4.8 squared Nine, oh, that's not 4.8 times 8. It's 23.04 plus negative 1.2 squared is 1.44 plus 7.8 squared is 60 divided by 5. Okay. Now I'm going to need to switch between a new whiteboard and this one. So I'm going to take this calculation and I'm going to put it on a new whiteboard. Okay. That probably is a little too messy for you. Let me just get this cleaned up here. 1.44 plus 60.84. Okay. All right. So now let's add up the numerator. Okay. The numerator 51.84 plus 17.64 plus 23.04 plus 1.44 plus 60.84 gives us 154.8. Okay, that's what I'm going to put on a new whiteboard. Okay, so sigma squared is equal to 154.8 divided by 5. Okay, 154.8 divided by 5, which gives us 30.96 for sigma squared. Okay, 30.96 for sigma squared. This is our population variance. Okay. Just to recap, right? Population variance, that is one of the major measures of dispersion we will be working with in this class. Population variance, sigma squared, right? This Greek letter is lowercase sigma, sigma squared. Population variance, sigma squared, is 30.96. That's telling us how spread out our data is. What's the dispersion of our IBM stock price? It's 30.96. Now, I mentioned that the two most common measures of location and measures of dispersion we're going to use in this class, right? Measure of location, it is the mean, right? Population mean, sample mean. The most popular measure of dispersion that we're going to use in this class, most popular measure of dispersion we're going to use is the standard deviation. So we need to get the population standard deviation. Okay. How do we get the population standard deviation? I mentioned. So the population standard deviation is just sigma. It's not sigma squared, right? The population variance is sigma squared. The population standard deviation is merely sigma. Okay. So sigma, population standard deviation, all we have to do in order to get the population variance from the population standard deviation, all we have to do is take the square root of sigma squared. That's all we have to do. Okay. In other words, the square root and the squared will cancel each other out. If the square root and the squared cancel each other out, then we would just be left with sigma equals sigma. Okay, sure, right? So again, we already know sigma squared, which is the population variance. But if we take the square root of it, then we'll just end up with sigma equals sigma. So in order to get the population standard deviation from the population variance, we just have to do the square root of 30.96, which equals 5 point something. I got to pull it up on my phone. I think the square root of 30.96 is 5.56. Okay. So 5.56. And that would be our population standard deviation. Okay. So what that's telling us, if we wanted to use, the IBM stock price example again, if you remember our data set, I'll put it up over here, right? Let me just write this down one more time for us. IBM price. Okay. It was 92, 95, 104, 98, and 107. Okay, so this is telling us that on average, okay, the true actual price of this population, right? Where's the center of it? The center of this data is located at $99.20. Okay. On average, the true actual mean of IBM stock price last week, whatever, I'm just making this up, right? But the true actual stock price of IBM on Monday, Tuesday, Wednesday, Thursday, Friday was $99.20. And it had a standard deviation of $5.56. So now we know where the center of the data is located, and we have an approximate scale or an interval that we can create to say, look, okay, well, check this out, right? We tend to think that 99 is the center, right? 99.2 is the center. And then we think that the price, pretty much fluctuates $5.56 down from 99 and $5.56 up from 99.2. So in other words, we think that the price tends to hover between 99 minus 5, that's 94, and 99 plus 5, which is 104. So we think that, most of the time the data is between $94 and $104. Yes, that appears to be the case. Okay. So what this is doing is, rather than looking at all the different speeds that you drive, right? It's telling us like, oh no, you tend to drive, 99 miles an hour with a dispersion of 5 miles an hour. Or another, the stock price tends to be $99, but it tends to go down, 550 or up 550. That's pretty much where this stock price hangs out, or pretty much where your speed hangs out. Or if we wanted to do height, we could say, all right, yeah, like on average, a male height tends to be 5 feet 9 inches tall with a standard deviation of 3 inches, right? So, on average, most men are between 5 feet 6 and 6 feet tall, right? Which sounds about right, give or take. That's what it's telling you. We have measures of location and then measures of dispersion. Okay, it tells you where the center of the data is located and then how spread out it is. Okay, so that's the population variance and the population standard deviation. It's sigma squared for the population variance, and it's sigma for the population standard deviation. Now I'm just going to create another whiteboard. I'm going to create another tab, right, in our whiteboards. Now let's calculate the sample variance and the sample standard deviation. Okay, so to do sample variance, we have S squared. Okay, remember, S squared, that is a English letter, right? So since it's S squared, we know we are dealing with a statistic. We also know it's a statistic because it's a sample, right? If it says sample, then we're working with a statistic. Statistics are characteristics of samples, okay? And then, of course, just the whole point of quantitative analysis, we're trying to estimate whether our statistics from our samples are reliable, reasonable indicators of our population parameters. Okay, and that's what we're doing here. So if we took our IBM stock price sample, okay, sorry, our IBM stock price population, excuse me, we had 92, 95, 104, 98, and 107. Okay. Let's say we want to make this our sample. Okay. Let's just take that as our sample. Okay. Well, now let's find out what the variance of this is. In order to find sample variance, what we're going to do is the summation of x sorry, I jumped the gun there. X the summation of x minus x bar squared divided by lowercase n minus 1. Okay, it's lowercase n minus 1. So when you get to the denominator, when you're doing sample variance, it's n minus 1. For population variance, it's capital N, divide by capital N. For the sample variance, we are doing n minus 1. So it's the number of observations minus 1. How many observations do we have? Here we have 92, 95, 104. We have 1, 2, 3 observations. So that will be 3 minus 1 equals 2. Okay. So again, however many observations you have, that's how many parentheses you have to have when you expand this formula, when you break it out, okay? So this is saying to summate all of the x terms that get subtracted by the sample mean and squared, okay? Well, that means that first we need to find, x bar. Well, excuse me, I'm jumping the gun again because we need to just see how we would actually expand this. So this is x1 minus x bar squared plus x2 minus x bar squared plus x3 minus x bar squared divided by n minus 1, which will be 2, right? We'll get to 2. But in order to actually calculate this, first thing we need to do is we need to get x bar, right? We need to get x bar. So how do we get x bar? X bar is the summation of x minus lowercase n, which equals 92 plus 95 plus 104 divided by 3. Okay. Just to be totally clear, totally transparent here, when we're calculating x bar, when we're trying to get the sample mean, right now we're trying to find the number that goes here. Okay? For this number, we divide by lowercase n. So we're dividing by 3. But when we get to here, and we do the sample variance, we're dividing by n minus 1. We'll be dividing by 2. So that's different. It's a little different thing. The denominators are different. Okay, so 95 plus 92 plus 104. Hit clear. 92. 95. Gives us 97. And again, I'm just going to double check this. 92 plus 95 equals plus 104. 291 divided by 3, 97. But we're good there. We have confirmation. Okay, now we're going to expand our formula. So S squared, the sample variance, is equal to x1, that's 92. 92 minus 97 squared plus 95 minus 97 squared plus 104 minus 97 squared divided by 3 minus 1, right? Number of observations in the sample. So n, 92, 95, 104. That's 3 minus 1, 2. Okay. 3 minus 1, 2. So what do we do next? We do the parentheses. 92 minus 97, that's negative 5 squared plus 95 minus 97, that's negative 2 squared plus 104 minus 97, that is 7 squared divided by 2. Okay. Negative 5 squared, that becomes, just to start it back over here again, that's 25 plus negative 2 squared is 4, right? That's negative 2 times negative 2. So that becomes 4, right? Negative 2 squared is 4 plus 7 squared. That's 7 times 7 is 49. Okay. 7 squared is 49 divided by 2. Our numerator becomes 29 plus 49. That's 60, 58. Divided by 2. And then 58 divided by 2, that's 25, 29. Okay. So our sample variance, S squared, is equal to 29. Okay. Now, if this is our sample variance, if the sample variance is 29, let's see what we get for sample standard deviation. Okay. Remember, the relationship between population, the relationship between a variance and a standard deviation is just if you take the square root of the variance, you get the standard deviation. So if you take the square root of the sample variance, the square root of the sample variance will turn into the sample standard deviation. So if we have S squared, which is equal to 29, okay, this is what we have. We already know that S squared is 29. Okay, let me write this a bit more accurately for us. The sample standard deviation is S. because S will be the square root of S squared. Okay. So the sample standard deviation S is going to be equal to the square root of S squared. Simple enough, right? The square root of S squared will become S. Well, if S squared is equal to 29, then S is equal to the square root of S squared, which is equal to the square root of 29, which means that S is equal to 5 point something. Square root of 29 is 5.38. Okay. So in other words, the sample standard deviation is 5.38. Okay. So now in closing, right, what we've done so far in chapter 3 here, we introduced probability distributions, we introduced measures of location, we introduced measures of dispersion. We saw that a probability distribution is simply nothing more than a combination of all the different values that a variable can take on and the relative likelihood of that occurring. We saw with our measures of location that we're looking at means, medians, and modes. And with our measures of dispersion, we're looking at ranges, variances, and standard deviations. Okay. The whole point of what we're trying to accomplish here is that we are trying to figure out if our sample estimates, if our sample statistics are indicative of our population parametric values. If the value of the statistics is fairly close to the value of the parameters. Well, let's take a look, right? I mean, for the sample standard deviation, we ended up with a value of $5.38, 5.38, right? Well, our population standard deviation was 5.56. So between 5.56 and 5.38, they're not exact, but they're somewhat close, right? Whether we want to consider that close or not is really the topic of the rest of the course, okay? Here we had a sample variance of $29, but our but our population standard deviation, our population variance was $30.96. Our sample variance was $29. Okay. So again, 30.96 versus 29. Is that close? Is it not? That's a topic for the rest of the class, right? Our sample mean is $97. If my memory serves me correctly, the population mean was $99.20. I think in another example, maybe our sample mean was $99. Okay. Well, $99 versus or $97 versus $99.20. Okay. Are those close or are they not? That is the point of the rest of the class. What quantitative analysis is doing is trying to determine, okay, is it reasonable now to think that this sample statistic is a good estimate of our population parameter? Okay, is it reasonable or unreasonable to think that? Okay, that's the whole point of the rest of the course. Now we have these tools, these measures of location, these measures of dispersion, and this understanding of what a probability distribution is. Now we have the tools we need to start to talk about whether these statistical estimates are good, reliable indicators of what our population parameters actually truly are. Okay, that's the whole point. So now that we possess these tools, we can move on and start looking at different probability calculations. And that's what the next sort of step in quantitative analysis becomes. So that's where I'm going to pick it up next.